Morning, everybody. My name is Zachary Zezius. I'm here with the rest of my team, Amy Drake, Charles Humphreys, and Hendra Alcantara. We are representing General Dynamics Electric Boat, and we're going to introduce you to our project, the Digital Twin. So, first things first, what is a digital twin? As Team Acumentrix pointed out earlier, a digital twin is essentially a virtual representation of a physical component. The thing that differentiates a digital twin from, say, a 3D model or a blueprint of a physical component is that it accurately represents all of the essential elements and variables of that physical component on the software side. It also has the ability to pull through real-time sensor data from that physical component into the digital twin. The utility of this is that the digital twin can take that real-time sensor information from the real world, pull it into the digital twin, and using a combination of historical data and predictive analytics, forecast the future performance and durability of your physical system. This has a lot of real-world applications, potentially. Our intended use case is in the field of predictive maintenance. The general idea is that rather than preventative maintenance, where you're kind of time replacing things in order to make sure that they never go wrong, or reactive maintenance, where you're waiting for something to go wrong before you swap out a component, you can use dynamic predictive maintenance in order to replace components just before they start to become a problem. This has clear implications for cost saving, but it also has the added advantage of minimizing the downtime of these components and anything that those components are installed on. In GDEB's case, this means that their submarines are going to spend less time in port undergoing maintenance and more time out at sea doing what they are supposed to do. So how did our team go about modeling our version of a digital twin? First thing we had to do was pick a physical system to model. We opted for a water pump, specifically Hayward Pool Products PowerFlow Matrix, which is an excellent pump for our purposes. The general gist of our methodology is that we run the pump through a series of stress tests, and we push it to the point of failure. While the pump is proceeding to the point of failure, we monitor its performance and durability with an array of sensors. Those sensors save the data that they collect to a database, and then we analyze that database with machine learning in order to build a model of our physical system and see how it performs under those conditions. By iterating over those tests and other similar tests multiple times, we can build a very accurate and reliable digital twin that can accurately predict performance of our physical system. But obviously, kind of tests are only as good as the data that you get for them. So on that topic, I'm going to pass you over to Amy Drake, who's going to walk you through the sensors that we use on our project.
So we chose our sensors based on a series of stress tests that we are going to run. The first one we chose is the accelerometer. The test that we are relating this to is shock and vibration tests. The temperature and humidity sensor, we chose a sensor based off of the test where we're going to essentially burn out the motor. And then we chose the water flow sensor based on doing a dry run of the pump. So for our project setup, we have a 55-gallon water drum, a pool hose, the water flow sensor, and the water pump. So this shows our whole entire circuit with the accelerometer, the temperature and humidity sensor, and the water flow sensor. For our project, we're going to have 3 accelerometers. There's going to be one on the pump, one on the pool hose, and then one just general for environmental data. We're also going to have 2 temperature and humidity sensors. One will be inside of the pump, and one will be on the outside to compare. And then we're also going to have a water flow sensor that will be connected to the pool hose. So some difficulties that we ran into. We originally had a vibration sensor instead of an accelerometer. And we decided not to use the vibration sensor because whenever we got it in, you had to shake it really, really hard, which for our application was not going to be useful because we wanted to be able to depict any slight movement that the pump was making. We also had issues with the sensor placement. So we wanted to place some of our sensors inside the pump. So one of the most difficult tasks was taking apart the entire pump. And as you can see in the photo, we have most of it taken off. With this, we decided the sensor placement is going to be on the easiest part to take off. So for when we get our future pumps, we will not be taking all of them apart. We also had problems with water leakage, mainly with our water flow sensor. So where our sensor is connected, it's connected to the pool hose. And through this, we added tape and different types of plumbing, cement, and everything, and it still leaks. So we drilled holes in the top of the water drum so that the water would drip back down into the drum. That being said, all these sensors will be used to collect data for the software aspect of our project.
Okay, so to describe the process and how we use our software architecture, first we decided to go with Python. Now, with digital twin being a new and complex concept to our group, we did a lot of research and we landed on Python because of its capabilities and many machine learning algorithms and applications in the real world. So starting us off, we have the water pump rather, with its sensors attached to it, and that's going to take in all of our data through the Raspberry Pi, and then the Raspberry Pi is going to take the data and send it out to our Postgres database on the Django framework. So moving forward and describing that in a step process, first you'll see on our left picture, we have our Raspberry Pi set up to our breadboard with a couple of sensors there, and we also have the water flow sensor on the right side as well to our 55-gallon drum. Now, the reason why we have those sensors on the outside is to take in the environmental variables and compare that with our water pump variables. And so we can actually see whether or not there's actually an anomaly within the water pump and see if there's any errors occurring. And then moving forward again, on the left side, you'll see our Raspberry Pi running our Python code that's searching for the specific GPIO pins for those sensors and also the proper credentials for the Postgres database, and then sending over all that data to our database on the Django framework. Now, if there's any type of error, it's going to notice that and either not save the data or not be able to connect to the server, obviously. And for optimization, we decided to restrict the Raspberry Pi to only taking in the data and then taking the data out and pushing it into the Postgres database. For further optimization, we decided to use the Postgres database because of the amount of data that we're going to need. As our friends in Acumetrics mentioned, we're going to need a lot of data for our digital twin process. So if we were to try to save it to a local disk, for example, or to like a USB hard drive, there's going to be speed limitations or a lot of limitations on storage capabilities. So that's why we decided to go with the database. Furthermore, we can also take that data and utilize it for a machine learning algorithm. Now, the machine learning algorithm will show us the predictive status of our pump, whether or not it's going to fail, and also it will pinpoint when it will fail and the failure points. Furthermore, we can use that same data for GUI, a graphical user interface, to show the user what is failing, where it's failing, and when it's going to fail if it's reaching that point. And it will also show us the plots of the data as we move forward with our project. Now, with that said, we still have a lot of work ahead of us in the spring semester. So to explain our anticipated best outcome, I'm going to hand you over to Hender.
To sum it up, we currently have a water pump with sensors installed, which is communicating to the Raspberry Pi. We have a database, which is gathering all the data and storing it. And we have the graphical user interface. However, in order for us to achieve the anticipated best outcome by the end of next semester, we have a few technical tasks left. Hardware-wise, we would like to set up the remaining pumps at Raspberry Pi. Ideally, we want to have 4 pumps running at the same time. This way, we can run different tests on them, and we can also use it. Next. We also would like to upgrade the pump assemblies. As you can see here, our setup is pretty large. We would like to make it more compact and mobile. We also need to conduct different failure test cases. This is vital to our project because this is how we'll be able to see trends and also pinpoint the failure points of the pump. Some of the test cases we like to run are dry running the pump, damaging the seals and the gaskets. We would like to contaminate the water supply. We would like to perform shock and vibration tests and also put the pump on the extreme temperatures. Software-wise, since we already have the database and the graphical user interface, we need to take all the data and graph it. That way, the user can see in real time how the pump is performing. After we have conducted all the test cases and we have enough data, we can use machine learning to analyze and actually predict when the pump will fail. That being said, would like to give special thanks to the following. And also, we would like to thank Hayward Pools for the anticipated donation of the pumps. Thank you.